K-nearest neighbors is really an incredibly useful algorithm. One of my favorite things about it is that it lends itself well to drawing pictures. We'll start by looking at using it for classification, being able to take a data point and say whether it belongs to category A or category B. Here, in this example, we're looking at mushrooms. So we're mushroom hunting, and we would like to be able to identify whether a mushroom is edible, safe to eat, or toxic, may kill us. Huge disclaimer, I know nothing about identifying mushrooms. Nothing here is factual or will help you identify safe mushrooms to eat. Notionally, this is a fun problem because a trained mushroom hunter can gather mushrooms that are delicious safely and avoid the ones that are toxic, even when the two are fairly similar, by being able to hone in on distinguishing characteristics. This is exactly what we want from a good classification algorithm. We want to be able to say, does this thing belong to category A, edible, or category B, toxic? And in this case, the consequences are quite severe. So in this imaginary world, the height and cap diameter of a number of mushrooms were collected. The ones known to be toxic are identified as crosses, and the ones known to be edible are identified with circles. You can see that there's definitely a pattern here, but there is no clean way to say mushrooms higher than a certain height are all toxic or all edible. Mushrooms with a cap diameter greater than a certain threshold are all toxic or all edible. The two groups are tight, but the boundary between them is wiggly and irregular. What we'd like to be able to do, the classification problem, is given a new mushroom where we know the height and we know the cap diameter, we'd like to be able to determine, is it toxic or edible? Can we use this set of examples to classify a new mushroom? The K-nearest neighbors approach is to look and find the closest neighbors to the point that we care about. K refers to the number of neighbors that we try to find. In this case, there are 5 neighbors within that circle. In practice, small numbers for K tend to work well. 5, 7, even 1, depending on your problem. Just look for the very closest neighbor. When working with a 2-class classification problem, so either toxic or edible, it's really convenient to have a K that's odd, because that way if you have 2 of one and 3 of the other, you can go with the one that has the largest number. One will always outvote the other. If you have 3 classes or more, then there's always a possibility of a tie. So you have to handle that tie in some way that makes sense given your data and the problem you're trying to solve. For now, we'll stick with a 2-class classification problem, and we'll stick with a K that's odd. So in this image, K is 5. All 5 of those neighbors are toxic. Therefore, KNN says a mushroom located at the plus sign with that cap diameter and that height will also be toxic. If we look at a different location, we can see where the plus sign is there with that cap diameter and that height, the 5 closest neighbors are all edible. So in that case, that would be predicted to be edible. In this location, the 5 closest neighbors includes 3 edible mushrooms and 2 toxic mushrooms. The edible outweighs the toxic, so that point would be declared edible. And you can see by looking at the plot that that definitely falls within the spread of the other edible mushrooms. So that's a very reasonable decision to make. Then, if we look at another point, if it includes, say, 4 edible mushrooms and 1 toxic mushrooms, definitely classified as edible. Here's one where we see a border case. In this location, we see a plus sign that seems to be very close to where the edible mushrooms are and the toxic mushrooms are. It technically includes 3 edible mushrooms and 2 toxic mushrooms, so it should be classified as edible. But if I'm looking at that, I'm thinking maybe that's going to be toxic. That's close enough to the rest that it might be toxic. So this is an example of where you may want to choose a different solution than a majority vote to determine your classification. That's a separate topic. We'll dive into that more in a later video. But this illustrates the concept of k nearest neighbors. You find the nearest k data points and you have them vote on what the winning category is. Now, the choice of k makes a difference. Let's say we also in this data set had an edible mushroom that we had found that has a cap diameter and height that places it out here amidst the other toxic mushrooms. Now, if we would like to know, if we would like to guess whether a mushroom with this cap diameter and height is toxic, we could say use a k of 1, find the closest neighbor, which is edible, and say, well, it's very close to this other edible mushroom that we found, so it's probably edible too. Now, if we have 100% confidence in our prior data and our labeling of that data, this is not a bad way to go. But if we have some noise in our data set and we think maybe some of our points are mislabeled, then this is not a good way to go because any mistake gets propagated. A way to protect against this is to have a larger k. So if we ramp that k up to be k equals 5, that just includes the edible mushroom and 4 toxic mushrooms. Those 4 toxic mushrooms will override the vote from that edible mushroom and it will be classified as toxic. So depending on what we believe about the accuracy of our data, that will affect the choice of k. A higher k does more correction for noise and inaccurate data points. A lower k gives us greater resolution. Another thing that makes a big difference in k nearest neighbors is how you scale your features. Let's imagine that on our mushrooms, we measured our cap diameter in centimeters, but our height in meters. What that would do effectively is squish all of our data down toward the x-axis. It's still perfectly valid. That's a valid measurement. It's still accurate. It's still conveying the same information. But if you look now, when you draw a circle around this particular point of interest, it captures, if you squint just barely, 1 toxic mushroom and 4 edible mushrooms. If we replot this exact same set of data and this exact circle with the height in centimeters instead, we get this really elongated ellipse that captures, just barely if you look closely, the 1 toxic mushroom and the 4 edible mushrooms. This, to casual eyeball, would clearly be a toxic mushroom. That plus sign is nested right down in there with the other toxic mushrooms, but because of how the features were scaled, it captured all of those other edible mushrooms above. The feature scaling matters. This means that when using k nearest neighbors, it's not enough to blindly feed your raw data into it, but that you have to think carefully about each dimension of your data and imagine a 1 unit difference in that dimension and try to estimate all of those dimensions and make sure a 1 unit difference means about the same thing in each case. An alternative, which we won't go into in detail here, is that you can learn a feature scaling. You can adapt and shift those feature scalings to give you the best possible results. I'm going to put a plug in here. The End-to-End Machine Learning Course 221 on k nearest neighbors walks through several examples of implementing KNN on different data sets, and one of the things we do is adaptive feature scaling. So if you'd like to walk through how to actually implement this in Python and have access to the code, please take a look at course 221 at End-to-End Machine Learning. Another thing that makes a difference in k-nearest neighbors is your distance metric. So not just feature scaling, but how you combine those features to make a distance. So imagine in our little space here with just two measurements, height and cap diameter, we have a circle here that represents our neighborhood, our closest neighbors. What this circle implies is that we're using an L2 norm. We're taking the height squared and the cap diameter, the difference in cap diameter, squared, adding it and taking the square root, and that's the distance. It's the Euclidean distance. It's the as the crow flies distance if you're looking at a map. It makes a nice circle. All of the points on that circle are an equal distance from that plus sign. But that's not the only way to make a distance metric. We could also take and just add up the individual dimensions. We could say the distance is the height in centimeters plus the cap diameter in centimeters, also known as the Manhattan distance or the Mahalanobis distance or the L1 norm. This is another perfectly valid way to create a distance. When working in just two dimensions, the L2 norm is a really convenient way to visualize distance. But when working with a lot of features, you get a very high dimensional space. There's some counterintuitive mathematical results that show that as the dimensionality of your space gets high, everything starts to gravitate toward being roughly the same distance apart in this L2 norm. But that's not true for the L1 norm. So if you have a high dimensional space, I really like the L1 norm for a distance. So this is something to consider when you're using k-nearest neighbors. If you're looking at, say, distances on a map, the L2 norm, the Euclidean distance, makes great sense to use because physically, that is the distance. That was the intuitive motivation for the notion of distance. But if you have a long laundry list of features, then the L1 norm or some other distance metric may be a better way to go. There are exotic distance metrics that you can use. I really like the L1 norm because it's so simple to explain and compute. We can use k-nearest neighbors not just with continuous data like height and diameter, but also with categorical data. So imagine now we're looking at mushrooms in a different way, and it's actually the cap diameter combined with the cap shape, whether it's indented or rounded, whether there's a little divot in the middle or it's nice and convex all the way across. This cap shape is a either or, the way we've represented it, categorical. It's either indented or rounded. And so that means all of our mushrooms either fall on this line that lines up on the next to indented or this line that lines up next to the rounded. And then the cap diameter is a continuous variable and it's spread across. If we want to use k-nearest neighbors here, we can do the same thing. We can treat it the same way. For instance, if we want to know, we find a mushroom in this location that's indented and it has this cap diameter, we'd like to guess whether it's toxic or edible. We look for, in this case, the 7 closest neighbors, k equals 7. We find 2 are toxic, 5 are edible. We can declare it edible. But don't forget, scaling matters. And in this case, what that means is the distance that those two lines are apart change the results that we get. Here's another example. If we're looking at this location and using k equals 5, we could look for the 5 closest neighbors and find that right here among the indented cap shapes, this mushroom would be projected to be edible. Even though an eyeball check says, you know what, it's sitting there among the indented cap shapes where all the rest are toxic, it's probably toxic. But this is an example of shifting the feature weight or the feature scaling so that the cap shape just doesn't carry much weight. And in that case, those other edible mushrooms with rounded tops would overpower the toxic mushrooms with indented tops and cause that position to be projected as edible. To repeat, feature scaling really matters, also with categorical data. We can also use k-nearest neighbors for regression. That is, if we don't want to assign a category to a data point, but we want to assign a value to a data point. Let's step back and say, now we're not interested in categorizing whether a mushroom is toxic or edible. We're interested in estimating the mass based on the height and the cap diameter. We've collected some data points for a given height and for a given cap diameter. The number represents the total mass of that mushroom. And you can see as the cap diameter gets larger, as the height gets larger, the mass gets larger. That makes sense. That makes sense all around. Now, if we want to look at a new point, we find a new mushroom, we know its height, we know its cap diameter, and we'd like to estimate its mass, we can use k-nearest neighbors to do that too. We look, for this case, k equals 5. We look at its 5 closest neighbors. We list all of their masses, 51, 52, 59, 67, 73, and we can take the average of that. In this case, that is 60.4. So by that scheme, we would estimate that this point has a mass of 60.4 grams. Now, looking at that, you might decide that's a good estimate. You might decide it's not. It is to the right of 67, but that 67 is already kind of low, between 51 and 59. So maybe that's about right. If we take a median, we get a 59, which is even lower than our 60.4. So maybe that's a better answer, maybe it's not. What you use depends on you. This is a choice that you get to make about the model. You can think of it as a hyperparameter. It's something that you choose, and the way to choose is you run them both on data that you already know, and you see which gives you the better result. So 2 equally valid ways to do it. A third way to do this is to take all those data points and weight their influence by how close they are to the point that you care about. So in this case, we do take our 5 closest neighbors, but some of those are much closer than others. 51, 52, 73 are kind of all out closer to the borders, to the edge of that circle. 59's in the middle. That 67 is really close. So using that, we give the closest data points the most weight. And if we weight this, then we might find that the weighted mean would be higher, closer to 67, maybe 66. Again, depending on the nature of the problem that you're solving, you can choose to use a weighted voting scheme. Such schemes exist for categorical data as well. You can, depending on how close the data points are, they can have a larger or a smaller vote. So k-nearest neighbors, in my opinion, is highly underrated. They have 0 training time. They're lazy, which means there's no model to train. All the calculation they do is when you ask it to do inference, when you ask it what the category of or the value of a new data point is. So that means there is no training time at all. Compare that to the hours or weeks or even computer centuries used to train other models, deep neural network models, for instance. Another great thing about k-nearest neighbors is sample efficiency, meaning that you don't have to collect very many data points before you're able to start making good, useful inferences about your space that you're working in. This, again, in contrast with, say, neural networks, where if you're doing categorization, you might need tens of thousands of examples of your data before you can start to reliably categorize new points into their classes. K-nearest neighbors is explainable. If you ask me why the algorithm picked a certain value at a certain point, I can point to the specific measurements around it that influenced it and tell you exactly how they contributed. That type of explainability is very rare. And if you're in a system where you need to know why a certain answer was arrived at, you can't do better than K-nearest neighbors. It's also incredibly easy to add and remove data. GPT-3 is a natural language processing approach. It's a neural network that I believe the state of the art requires hundreds of millions of dollars of compute time to train. If you wanted to remove the influence of one piece of text from that data, you would have to take it out of your data set, out of your training set, and retrain the whole thing at the cost of another multi-hundred million dollar check. It's just not feasible to do. Also, if you want to add new data, you have to add it and then retrain it. Now that's a little bit dramatic. There are ways to shortchange that a little bit, but not much. There is a lot of retraining you have to do every time you change your training data set. With K-nearest neighbors, it's easy. You just add or remove the data point from your collection, and the next time you go to make an inference, it won't be there, or the new one will, and you'll get a slightly different result. It is trivial to modify the data to tell, say, someone who was represented by the data, who wanted their data point deleted, that, yep, we deleted your data. It will no longer be reflected in the model in any way. It's very nice to be able to say that with confidence, with certainty, and to be able to demonstrate to an audience how that is done and why that's the case. Another more subtle element that is nice about K-nearest neighbors is they're less sensitive to class imbalance, at least global class imbalance. Let's say we had a data set that had 1,000 edible mushrooms and just 10 poisonous ones. Then K-nearest neighbors is okay with that, as long as locally, within the neighborhood of any new mushroom that we collected, there was a nice representation of any edible and toxic mushrooms that happen to be close to it. As long as the local density is balanced, the global imbalance doesn't really matter. So that's a rare property among machine learning algorithms as well. Now, it's not without weaknesses. No algorithm is perfect. Everything has trade-offs. So K-nearest neighbors, it's expensive to compute. If you have a lot of data points and you have to find the 5 closest, it means you have to figure out how close all of them are so you can find the 5 that are the closest. And calculating that distance can get very expensive if you have billions of data points. Also, as we've called out, it's sensitive to feature scaling and it's sensitive to your choice of distance metric. So you have to get those right or you can get really nonsensical answers. Now, fortunately, there are workarounds for the weaknesses, so you can make it work for you. As we called out, you can do learned feature scaling. Even though it is expensive to compute the distance for the whole data set, there are clever data structures like KD trees and ball trees that I won't go into right this moment, but what they allow you to do is just compute the distance for a small chunk of the data. It lets you say, hey, I'm looking for a data point in this region, and then it lets you focus on the data points in that region and just calculate the distance to all of them. And you can use that to save the huge computation of computing the distance to all of your data points. Also, there's this really clever thing called data reduction. If I have 10,000 edible mushrooms, but let's say that 500 of them are nearly identical, I can throw most of them out and just keep one good exemplar, one good prototype that shows what I'm looking for there. And that way, when I have a new one that I want to check out, if it's similar to that, it'll be able to pick it up by K-nearest neighbors, but I don't have to keep all 500 examples of it. So by doing clever data reduction, making sure that the examples you keep are spread nice and evenly across your feature space, you can still get very high quality answers, but at a small fraction of the data storage and compute requirements. I will call out that methods for doing data reduction are a topic of active research. This is not a solved problem. Good data reduction methods depend very much on the nature of the data and the problem you're trying to solve. But here's a plug for if you're looking for a good data algorithmic research topic, you could do a lot worse than efficient data reduction in K-nearest neighbors. I hope I've sold you on the fact that K-nearest neighbors is a solid machine learning algorithm. It doesn't get as much love as deep neural networks, but it should. It is robust. It is the crescent wrench of the toolbox. It works pretty well on almost everything if approached carefully. If you'd like to learn more about it, I have a course that I mentioned, course 221 in end-to-end machine learning, where we code it up from scratch in Python. We apply it to 4 different data sets, one with penguins, one with zoo animals, one with diamonds, and one with interpolating elevation in maps. And we show how to implement some of these things like automatic feature scaling that lets you step up your K-nearest neighbors performance. Thanks for tuning in.
Bayesian inference is a way to make guesses about what your data mean based on sometimes very little data. The way it works is tricky, but it's not magic. It's definitely something that you can wrap your head around, and it's not impossible to do so. My goal is that by the time we're done talking, you'll have a pretty crisp picture of how it works. Bayesian inference is just guessing in the style of Thomas Bayes, who was a nonconformist Presbyterian minister. He wrote a couple of books, one about religion and one about probability. So Bayesian inference is just guessing in the style of Bayes. So to illustrate it, imagine that you're at the movies and someone drops a ticket. You pick it up and you can see them from behind. You know they have long hair, but you don't know whether they're a man or a woman, so you have to make a guess. Based on what you know about the attendees at your movie theater, you might say, "Excuse me, ma'am, is this your ticket?" Now imagine instead that this person is standing in line for the men's restroom. Knowing this extra piece of information, you might make a different guess. Bayesian inference is a way to capture this common sense knowledge about the situation and help you to make better guesses. So to put numbers to this dilemma at the movie theater, let's assume out of 100 women at the movies, 50 have short hair, 50 have long, and out of 100 men at the movies, 96 have short hair and 4 have long. In this case, we can see that there are definitely more women with long hair than men with long hair. So it's a safe bet to assume this person's a woman. Now we just made a subtle assumption that there are about the same number of men and women at the movies. This assumption no longer holds when we move to the men's restroom line. Here, let's say there are 2 women out of every 100 people and 98 men, maybe women keeping their partners company. There's still one with short hair and one with long hair. It's still half and half long and short hair, but now there are 4 times as many men with long hair than women with long hair in this group. Now the safe money is to bet that this person is a man. So to draw this a little differently, out of 100 people at the movies overall, we'll make this assumption explicit that 50 of them are women, 50 of them are men, so this is how the different categories break down. In the line for the men's restroom then, they break down a little differently. So to translate this to math, the probability that a person is a woman is the total number of women divided by the total number of people, 50%. Similarly for men. Moving to the men's restroom line, the probability that someone is a woman is 2%, 98% for men. Now, Bayes' theorem is a little bit tricky, so to be very precise, we're going to have to talk math. So if you bear with me for just 3 probability concepts, we'll lay the foundation for presenting Bayes' theorem. The first one is conditional probabilities. If I know that a person is a woman, that's the condition, what's the probability that that person has long hair? So it's written as probability of long hair given that a person's a woman. So to get this, we just divide the number of women with long hair by the total number of women, 50%. And this doesn't change whether there's 50 women in your group or 2 women in the group. Still, if we know that a person is a woman, the probability that they have long hair is 50%. We can do the same thing with men. Probability that someone has long hair given that they're a man is 4%. So conditional probabilities, if I know that B is the case, what's the probability that A is also the case? This is not, you can't reverse B and A and have this be true. So for instance, if I know that the thing I'm holding is a puppy, what's the probability that it's cute? The probability is very high. If I know that the thing I'm holding is cute, what's the probability that it's a puppy? Well, it might be a puppy, it might be a kitten, it might be a hedgehog, it might be a small human. There's lots of things that it could be. So the probability there is less moderate. So these things are not interchangeable in conditional probabilities. Now, concept 2, joint probabilities. So what's the probability that a person is both a woman and has short hair? So to calculate a joint probability, you first find their conditional probability. Well, if I know that they're a woman, what's the probability that they have short hair? And then you multiply that by the probability that they're a woman. So in this case, 0.5 times 0.5, we get a 0.25, which is exactly what we knew it was going to be. And the same is true for all of our different conditions. So we can do this for the men's restroom too. The probability that someone is a man and has long hair, 4%. Someone is a woman and has long hair, 1%. Joint probabilities are different than conditional probabilities. Here, the probability that A and B is the case is the same that the probability that B and A is the case. So the probability that I'm having a jelly donut with my milk is the same as the probability that I'm having a milk with my jelly donut. These two conditions, these two situations are identical, so we can swap the order. And finally, concept 3, marginal probabilities. If I wanted to say figure out the probability that someone has long hair, I just add up all of the different ways that someone can have long hair. They can be a woman with long hair or a man with long hair. In the men's restroom line, that's a 1% probability plus a 4% probability, or a 5% probability overall. And you can do the same thing for short hair, 95%. Now, this last concept finishes our foundation. We can get to what we really care about. We know that this person has long hair. What's the probability that they are a man or a woman? This is a conditional probability, but it's the reverse of the one that we know. And we don't know how to answer this yet. So, this is where Thomas Bayes comes in. He noticed something really cool. You can calculate the joint probability that someone is a man and has long hair using the formula we saw before. And you can also calculate the joint probability that someone has long hair and is a man. Now, these are different formulas, but remember, joint probabilities don't care about the order. So these two things are equal, which means the stuff that they're equal to on the other side are also equal to each other. And we can do a little algebraic sleight of hand. And now we have a formula for what we want to know. If someone has long hair, what's the probability that they're a man? And we have this expression to the right. We can genericize that with A's and B's, and now we have Bayes' theorem, one of the top 10 most popular math tattoos of all time. So using this formula, we can go back to the movie theater and plug in what we know. We know that the probability that someone is a man. We know the probability that if they're a man, they have long hair. And we know the conditional probability marginal probability that someone has long hair, which is just the probability that someone's a woman with long hair plus the probability that someone's a man with long hair. And we plug all that in, and we can say if someone has long hair at the movie theaters, there is a 7% chance that they are a man. Similarly, 93% chance that they are a woman. Now, if they're in line for the men's restroom, because some of those probabilities change, that conditional probability changes. Someone's in line for the men's restroom and has long hair, there's an 80% chance that they are a man. And this is consistent with what we saw before. We know that there are 4 men and 1 woman for every 100 people in line for the men's restroom that have long hair. So 4 out of 5 long-haired people are men, 80%. It all adds up. So this example shows the mechanics of how to get Bayes' theorem and how it works. In practice, it's usually used a little differently. So to show this, we'll have to do a little bit of a detour and first talk about probability distributions. You can think of probability like a pot with just 1 cup of coffee in it. You can fill up, if you just have 1 cup to fill up, you can fill it all the way to the top. But if you have more than 1 cup, you have to share it around or distribute it. And you can share it in any proportion you want. So for instance, if we're representing the number of men and women at the movies, we could share it 50-50, but it'll always add up to 100%. We could even share it further into different categories. So here we see the joint probabilities of all of our 4 different categories that we were working with. And you can see that this is just another representation of the distribution representation that we were looking at before. Now usually when we look at this, they're side by side, probability instead of percentage, and shown in a histogram like this. It can be really helpful to think of these as beliefs. So for instance, if I flip a coin and hide the result from you, you might half believe it's heads and half believe it's tails until I tell you what it is. If I roll a die and hide the result from you, you might believe about 1/6 that it's a 1 or a 2 or a 3 or 4 or 5 or 6 until I show you the result. So these are what you believe. Probabilities can represent what you believe about something before you measure it. Similarly for Powerball tickets, and even for things that are more complicated, like let's say the height of adults in the United States in centimeters. You might believe that there's a very small chance that they'll be over 210 centimeters and a smallish chance that they're less than 150 centimeters, and then assign various amounts of this belief to all of the ranges in between. It still adds up to 1. It's like a bunch of cups of coffee lined up in a row, and you put a little bit in each one. The cups in the middle have more. And it shows how your belief about some individual is distributed before you've actually measured them. Now you can take these bins and chop them more and more finely, again and again, and if you keep doing this, you can get to something that's actually perfectly smooth. So it's as if you had an infinite number of very tiny cups and you put a tiny bit, infinitesimal amount of coffee in each one. At this point, it's probably no longer helpful to think of it in that terms, but just thinking of it as a continuous distribution, showing for all these heights, where am I placing my bets? What do I believe and how much? So once you have your beliefs, you can use it to answer questions about typical heights, the average, the median value, the most common value, or the mode. Now we'll use this in weighing my dog. I have a Shih Tzu named Reign of Terror. She's a little mischievous, and when we go to the veterinarian, Reign squirms on the scale. So every time we weigh her, we get a different weight. This last time we got 13.9 pounds, 17.5 pounds, and 14.1 pounds. What we want to know is how much Rain weighs. And this will be the basis for a decision. This is important. If her weight has gone up, her food intake will have to go down. And for her, this is a matter of life and death. So we don't want to make the wrong assumption and draw the wrong conclusion. So if you've ever taken a statistics class before, you know you can take these measurements, add them up, get the average, 15.2 pounds. You can calculate the standard deviation of these three measurements and also the standard error and come up with a 1.16 pound standard error, which when you show it graphically, this red curve now shows the belief that results from those three measurements, the distribution. The peak of that hill is at 15.2 pounds, and one standard deviation on that curve is our standard error of 1.2 pounds. So you can see looking at this that yes, it's most likely that she's 15.2 pounds, but there's a lot of that curve that sits outside of the range of 14 to 16. So yeah, she's probably between 14 and 16 pounds, most likely between 13 and 17 pounds, but she might even be lower than 12 and higher than 18. That is a really wide range, and it's not a great basis for making a decision. Now you can see the three measurements there, those three white vertical lines, and you can see why our belief is so dispersed, because those three measurements are pretty dispersed. It's hard to capture all that in one distribution. So let's try it again with Bayes' theorem. So the way we'll do this is, instead of A and B, we'll substitute in W for her actual weight and M for the measurements that we took. Now this term over here, the probability distribution of the actual weight, is our prior. This is what we believe about her weight before we put her on the scale. The probability given a weight of getting certain measurements are the likelihood associated with those measurements. And then the posterior is what we believe about her weight given those measurements. So you can think of this as we start with a belief, we take some measurements and we update it, and then we have a new belief when we're done. This term on the bottom we're going to ignore for the most part. It'll be a constant, but it's called the marginal likelihood. So we're going to start by not assuming anything about her weight. Could be 1 pound, 10 pounds, 20 pounds, 100 pounds. We're going to let this be uniform and we're going to let the data speak. So now our formula looks like this. We can further simplify it. And so we want to calculate this. We want to calculate the probability of our measurements occurring given a weight. And we want to do this for all of the possible weights. And then we'll end up with a new distribution, which is our belief. What's the probability of each of those weights occurring given the measurements? So these two things are identical. So let's start, for instance, by assuming, what if she weighed 17 pounds in reality? Now, because our measurement process is very noisy, as we saw, if she weighed 17 pounds, we would expect those measurements to be distributed as shown here. Some would be up way above 18 pounds, some would be down around 14 pounds, where we actually measured, but not very many of them would be. So to calculate now the probability of our measurements occurring, given this weight, we find what the probability of each individual weight is of occurring, and we multiply that times that times that. Now these two are pretty small. When you multiply two small things together, they make something very small. So the probability of her being at 17 pounds is pretty small. We shift our belief over and say, well, what if she was 16.5 pounds? What if she was 16 pounds? And we recalculate it each time, multiplying all of those actual probabilities together. And then by the time we're done, this is what we've measured at each of those weights. This is the likelihood of each of those occurring. And you can see that the maximum likelihood occurs at 15.2 pounds. And this is commonly called the maximum likelihood estimate, where you start with uniform assumptions on your weight. And it just so happens that the standard error on this is exactly what we calculated before. A very cool connection here. When you take the average and calculate standard deviation and standard error, it gives you the likelihood that you would get by doing Bayes' method and assuming a uniform prior, not assuming anything about what the result's going to be. So, we've already established, though, that that's a really broad result and not helpful. So we need to start over now, and let's start with what we know. So some background information. Rain was 14.2 pounds the last time we went into the vet. And she doesn't seem noticeably more heavy to me. My arm is not that well calibrated, but I'm going to assume that she's within about a pound of where she was before. So I take that prior, and this is the form that it takes. A normal distribution centered on 14.2 pounds, and you can see that most of that bulk is within plus or minus a pound. And it extends a little bit further out. Allow for the possibility that she's actually gained a lot or lost a lot of weight, but probably she's pretty close. This is what I believe before I even put her on the scale. This is the probability, the probability of her being a given weight. So this time we're not neglecting the prior term. We're not setting it constant. We're going to use it. And the way this plays out now is we assume, okay, what if she were 17 pounds? Well, we need to multiply that now by the probability of our prior showing that she's 17 pounds, which actually makes that quite small. Now we calculate and multiply the three probabilities of our measurements occurring. So now we have something small times something very small times something very small. So we get a very small result probability that she actually weighs 17 pounds. And now we repeat this process at 16.5 pounds and 16 pounds and 15.5 pounds and 15 pounds all the way through. And then by the time we're done, we tally up all of those and we get this new posterior distribution. It's normally distributed at about 14.1 pounds, and it has a standard error of less than a pound. You'll notice it's even narrower than our original prior. So we've taken our original belief and we've been able to sharpen it up just a bit. And so incidentally, the peak of this curve is called the maximum a posteriori result. If we had to choose one value to represent our belief, that's not a bad one to choose. And now we compare this with our original estimate. It's labeled non-Bayesian here, but more accurately it could be Bayesian with a uniform prior. You can see that it is much broader, and also the peak of that curve is in an entirely different place. So the answer that we got, it's more confident because it's more centered, and it's probably, based on what we know, closer to being correct. So this is how Bayes' theorem is used most often in data science or in analysis. It's a prior that you then update based on your measurements to sharpen up and get a revised set of beliefs. So there's a lot of times that it makes sense to use Bayesian inference. Sometimes we just know things. Like if we're measuring age, we know that everyone is more than 0 years old. And so we can take that information and build it in, and we can get sharper estimates with fewer measurements. Now, so it should, if you're paying attention, make you a little bit nervous. We humans are actually not always aware of what we believe, and putting it into a mathematical distribution can be very tricky. More importantly, The reason we're measuring something is because we want to learn about it. We want to be able to be surprised by our data. So if we believe something that's not true, it can make it hard or impossible to learn from our data. I like how Mark Twain phrased this. He says, "It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so." So the way to avoid this pitfall is to always believe things that we think are impossible, at least just a little bit. So by leaving this room for something to be possible, we can do like Sherlock Holmes says, and once you've excluded the impossible, then whatever remains, however improbable, must be the truth. We don't want to exclude the improbable out of hand, because then we're left with nothing. Alice, in a conversation with the Red Queen, summed it up well too. "There's no use in trying," she said. "One can't believe impossible things." "I dare say you haven't had much practice," said the Queen. "When I was younger, I always did it for half an hour a day. Why, sometimes I've believed as many as 6 impossible things before breakfast." So the secret to using Bayesian inference well is to keep believing impossible things. Thanks for your attention. Here's how you can get in touch with me if you'd like to carry on the conversation. I look forward to talking with you again soon.
Hi, this is Brandon Rohrer with How Decision Trees Work. Decision trees are one of my favorite models. They're simple and they're powerful. In fact, most high-performing Kaggle entries are a combination of XGBoost, which is a variant of decision tree, and some very clever feature engineering. The concept behind decision trees is refreshingly straightforward. Imagine creating a data set by recording the time you left your house and noting whether you arrived at work on time. Looking at it, you can see that for the most part, departure times before 8:15 result in punctuality, and departure times after 8:15 result in tardiness. You can summarize this pattern in a decision tree. The very first branching point is the question, did departure occur before 8:15? There are 2 branches, a yes and a no. For consistency, we'll keep all of our yeses on the left. Placing this decision boundary divides the data up into 2 groups. And although there are some stragglers and exceptions, the overall pattern is captured by placing this decision boundary at 8:15. If you depart before 8:15, you can be reasonably sure of getting to work on time. And if you depart after 8:15, you can be reasonably sure of being late. This is the simplest decision tree possible, a single branch. We can refine our estimate of punctuality by subdividing both the before 8:15 and the after 8:15 branches. If we add additional decision boundaries at 8 o'clock and 8:30, then we can divide up our arrival estimate more fully. Those before 8 o'clock are confidently on time. Those between 8 and 8:15 are probably on time, but not guaranteed to be so. Similarly, departure times after 8:15 can be divided into those after 8:30, which are almost certainly late, and those before 8:30, which still have a small chance of being on time. This decision tree has 2 levels. Decision trees can have as many levels as you want. Most often, each decision point or node has only 2 branches. This example has a single predictor variable and a categorical target variable. The predictor variable is our departure time, and our target variable is our punctuality, whether or not we're late. Because it has only 2 distinct values, it's categorical. Decision trees with categorical targets are also called classification trees. We can extend this example to the case where there are 2 predictor variables. Consider both the departure time and the day of the week. We'll start counting at Monday equals 1, so Saturday equals 6 and Sunday equals 7. Inspecting the data, we can see that on Saturday and Sunday, the green-filled donuts, representing being late, extend further to the left. This means that leaving at 8:10 is probably sufficient to get you to work on time on a weekday, but probably not on the weekend. To represent this in a decision tree, we can start as we did before by putting a decision boundary at 8:15. Any departure times after 8:15 are likely to be late. Departure times before 8:15 are inconsistent. Before, we assumed that they would be on time, but now we can see in the data that that's not entirely true. To make our estimate better for the weekends, we can subdivide the before 8:15 departure times into weekday and weekend. Now, a weekday departure before 8:15 is confidently on time. However, weekend departures before 8:15 are mostly on time, but not entirely. We have updated the decision tree with a node that reflects this new decision boundary. Now we can further refine our estimate by subdividing our weekend pre-8:15 departure times into before and after 8 o'clock. Before 8 o'clock, almost all of the arrivals are on time, and between 8 and 8:15, the majority of them are late. Now we have our two-dimensional decision tree neatly divided into 4 regions. 2 of them reflect on-time arrivals, and 2 of them show late arrivals. This is a 3-level decision tree now. Note that not all the branches need to extend down to the same number of levels. Now we can look at an example with a continuous target variable rather than a categorical one. When a model is used to make predictions about continuous numerical variables, it's also called a regression tree. So far we have looked at 1- and 2-dimensional classification trees. Now we'll look at regression trees. Let's consider the question of what time someone wakes up, as predicted by their age. The root of our regression tree is an estimate for the entire data set. In this case, if you had to make an estimate without knowing someone's age, a reasonable guess would be 625. This is the root of the decision tree. A reasonable first split is at age 25. On average, people younger than 25 wake up at 7:05, and people older than 25 wake up at 6 o'clock. There's still a lot of variation in the younger group, so we can split it again. Now the people younger than 12 can be estimated to wake up at 7:45, and people between 12 and 25 can be estimated to wake up at 6:40. The over 25 group can be meaningfully subdivided too. Those between 25 and 40 wake up on average at 6:10, and those between 40 and 70 wake up on average at 5:50. There's still a lot of variation in the youngest group, so we can further subdivide it. By slicing again on age 8, we can refine the estimates to more closely fit the data. We can also subdivide the 40 to 70 group on the 58-year line. Notice that we're getting to where we only have 1 or 2 data points per leaf of our tree. This is a dangerous condition and can lead to overfitting, which we'll talk more about in a minute. The resulting tree lets us make a numerical estimate depending on someone's age. If I need to estimate the wake-up time for a 36-year-old, for instance, I can start at the top of the tree. Are they younger than 25? No. Go to the right. Are they younger than 40? Yes. Go to the left. The estimate then becomes 6:10 a.m. The structure of the decision tree lets you sort people of any age into their respective bin and make an estimate about their wake-up time. We can also extend this regression tree example to have 2 predictor variables. If we consider not only someone's age, but the month of the year as well, then we can find even richer patterns. In North America, days are longer in summer months, and it gets lighter earlier in the morning. In this completely unrealistic example, children and teens are unburdened by the rigorous schedules of work and school and have their wake-up time driven by when the sun comes up. On the other hand, adults fall into more regular patterns, fluctuating only slightly with the seasons. Again, older people in this example tend to wake up a little earlier. We construct this decision tree much the same as the last one. We start with the root, a single estimate that roughly fits the entire data set, 630. Then we look for a good place to put a decision boundary. We split the data on age 35, creating two halves, one for our under 35 population with a wake-up time of 7:06, and one for our over 35 population with a wake-up time of 6:12. We repeat the process, subdividing our younger population on whether it is before or after the middle of September, and whether it is before or after the middle of March. This isolates the winter months from the summer months. Winter months have a wake-up time of 7:30 for those under 35, and in the summer months it's 6:56. Then we can revisit our over 35 population and split them again on age 48 to get a more accurate representation. We can also go back and subdivide our under 35 winter wake-up times on age 18. Someone under 18 in the winter will wake up at 7:54 as opposed to 6:48 for those over 18. You can start to see the emergence of the tall corner peaks. As we make each additional cut, the shape of our decision tree becomes a little bit closer to that of the original data. Also, you'll notice in the upper right-hand plot that the decision boundaries begin to slice the dataset into regions of approximately uniform color. The next cut continues this trend, focusing on dividing those younger than 35 in summer months to those older and younger than 13. The shape of the model becomes even more similar to that of the data. You can imagine continuing this process until the model closely represents the smooth trend underlying the data. Each decision region would become progressively smaller. The approximation to the underlying function in the data would become progressively better. The power of decision trees is not without pitfalls. An important one to watch out for is overfitting. Returning to our example of a single variable regression tree, age versus wake-up time, imagine that we continued to make cuts on the age axis until there were only one or two data points in each bucket. When we get to this point, the decision tree explains and fits the data very well. It fits too well. Not only does it capture the underlying trend, the smooth curve that the data follows, but it also catches the noise, the unmodeled variation that's included in the measured data. If we were to take this model and use it to make predictions about new data, the noise from the training data would actually make our predictions less accurate. Ideally, we want a decision tree to capture the underlying trend, but not to capture the noise. One way to safeguard against this is to make sure that there are more than a handful of data points in each leaf of our decision tree. That way, any noise will be able to average itself out. Another thing to watch out for is having lots of variables. We started with a one-dimensional regression tree, then included month data to create a two-dimensional regression tree. Decision trees don't care how many dimensions we have. We could, for instance, also add latitude, the amount of exercise someone gets on a given day, their body mass index, and any other variables that we think might be relevant. To visualize this, we'll use a trick shared by Jeffrey Hinton, a renowned deep neural network researcher. He recommends, to deal with hyperplanes in a 14-dimensional space, visualize a 3D space and say 14 to yourself very loudly. The challenge when working with many variables then becomes deciding which variable to branch on when growing our decision tree. If there are very many variables, then this can require a lot of computation. Also, the more variables we add, the more data we need to reliably choose between them. It's easy to get into a position where the number of data points is comparable to the number of variables. When our data set is represented as a table, this manifests itself as the number of rows being comparable to the number of columns. There are methods for dealing with this, such as randomly selecting a variable to divide on at each branch, but it's something to keep an eye out for and handle mindfully. As long as you keep your eyes open for places where decision trees might fail, you're free to take advantage of their strengths. Decision trees are fantastic for when you want to make as few assumptions about your data as possible. They're quite general. They can find nonlinear relationships between your predictor variables and your target variable, as well as nonlinear interactions between predictor variables. Quadratic, exponential, cyclical, and any other relationships can all be revealed as long as you have enough data to support all the necessary cuts. Decision trees can also find non-smooth behaviors, sudden jumps, and peaks that other models like linear regression or artificial neural networks can hide sometimes. There's a good reason that decision trees consistently outperform other methods on data-rich problems. Thanks for tuning in, and I hope this is helpful in building your next project. You can learn to drive a car by getting the keys, having someone show you how the steering wheel, the gas, and the brakes work. Try it out in a quiet parking lot, and then ease yourself onto the open road. And before long, you're able to get yourself to the grocery store and to a friend's house, and you can get done the basics. Now, contrast that with becoming a race car driver. In that case, you want to be able to get as much performance as possible out of your car. And to do that, you need to know how it works down to the nuts and bolts. That's the process of looking under the hood or opening the black box. If you want to get the most out of your tools, then how things work really matters. So to show you what I mean by this, for most of us, beginning machine learning or software engineers, this is what a support vector machine looks like. Here is the black box. You import scikit-learn, queue up a simple example and run it, and you're done. Here are the keys, here's the steering wheel, go. But to get the most out of it, you have to go deeper. My goal in this talk is to walk you through the process of going deeper, but more importantly, to show how any of us can go deep on any subject that we want to master. So as I tackled support vector machines, which were fairly new to me when I started this presentation, the first step I took was to read the scikit-learn documentation. This is what I came across. It's not particularly helpful to me being new to support vector machines. It's a nice, concise summary of the basic principles of how they work, but it doesn't explain it to someone who doesn't already know them well. One thing that the scikit-learn documents did provide was this great diagram showing here two different colors of points being separated by a line. That line looks kind of like a road where those two lanes are as wide as they can possibly get before they start touching data points. This was helpful. My next step was to go find a nice tutorial and read it. I found one that was highly recommended and started reading through it. And I saw definitions and tables and equations and graphs and diagrams and plots, and very soon got very overwhelmed, and there were theorems, for God's sake. And I felt strongly that it was probably important stuff, but it was not very accessible to someone who is new to the topic. So I took a step back, I set that aside, and I went to YouTube. And I pulled up some of the most popular videos on support vector machines, and in the course of doing this, saw multiple explanations of what they are, what they're used for, how to visualize them, how the math underneath them works. And the principles finally started to click. They began becoming clear in my brain. Following this, I went and found some more blog posts, again from a variety of posters, each with their own way of visualizing how they work, of explaining the principles behind it, and now the equations and the math and the definitions started to make a little sense. Enough so that I, in the next step, started to try to explain it to myself. And the way I do this is by drawing pictures. And so I started illustrating some of these concepts in a way that would make sense to me in my brain. Now that the ideas underneath support vector machines, at this stage, they're crystals, they're nuggets, but they're a scaffold, but they're not fleshed out. So to do this, I find it very helpful to choose a toy example. This is a bit of an art, it's trial and error, but finding an example that's simple enough that you understand it completely and you know exactly how it should work, but it's just complicated enough to illustrate the principle. So for this one, I settled on fruit. So imagine that we have fruit. It can either be small or large or yellow or purple. Now, any small fruit is a plum. If it's yellow, it's not yet ripe, but if it's purple, it's ripe and good to eat. Any large fruit is a peach. If it's yellow, it's great to eat, but if it's purple, it's rotten. You don't want to eat it. So in this example, we have in the world of peaches, there's a size axis and a color axis, and you can see the good things to eat are at the upper left and the lower right. Now, in this example, once you have this example, if you can get it to where you can explain it to, roughly like a 12-year-old, a 6th grader, which means that you use words and ideas that are common, no jargon, or if you do use a jargon term, you explain it thoroughly. So here's my attempt to do that for support vector machines. So imagine you have peaches, and they can be any color between yellow and purple, and you would like to figure out which ones are good to eat. You'd like to know, in fact, if you get a new peach, based on its color, whether you should eat it or not. So what you do is you get a bunch of peaches, and you grab one and you try it. You get one that happens to be yellow, you taste it, it's good. So you make a green circle and put it at the point that represents its color. You grab another one that's pretty purple and you taste it and it's nasty, it's rotten. So you put a black X at the point that represents its color. And you do this again for a few more peaches, some yellow ones, some purple ones, some ones in between. And before long you have a data set that looks like this. The green circles all show good peaches, the black X's show bad peaches. Now that you have all this data, you would like to make a prediction. Based on a peach's color, do you expect it to be good to eat? Support vector machines allow you to do this. And what they do when you have two groups of data is they come and they put what looks like a road in between them. There's a dotted center line and then two lanes, and it tries to make that road as wide as it can possibly get until the outside of those two lanes bump up against your two data sets. The center line is the divider between the two groups. Anything to the left of that will be assumed to be good to eat. Anything to the right of that will be assumed to be bad to eat. And the lanes on either side are called margins, for lack of a better term. Now, imagine though that in this set of peaches, this can be trickier. What if you have some that don't really fall with the group? You get some yellow peaches that just don't taste right, or you get a purple peach that for some reason tastes amazing. Now the data set, there's nowhere you can draw a line that separates the green circles from the black X's. But what you can do is still create a dividing line with its margins, but any data point that is on the wrong side of its margin gets a penalty based on how far it is over. And so you can move the position of this dividing line and the width of its margins to take that penalty and add that penalty in and still make that as small as you possibly can. So you can still use support vector machines in cases where your data isn't completely separate. The fancy term for that is linearly separable. Just means you can't separate it with a line. So it can handle non-linearly separable data. Now let's look at a different case. Instead of just peaches, we have peaches and plums. The good ones, we either want to eat yellow peaches or purple plums. A yellow plum isn't ripe and a purple peach is rotten. So we can do the same thing in this world. We try a bunch of fruit of different sizes and different colors. We find that the yellow peaches are delicious. We find that the purple plums are delicious, but the yellow plums are terrible and the black peaches, the purple peaches are terrible. So we end up with a data set that looks like this. The challenge now is that if we try to draw a line to separate these out, it's not just that a few data points are going to be a little bit off. There's a whole chunk of our data that we're missing. We're not capturing it well. So this data is obviously not linearly separable. To help us visualize this, I went and took it into Python and made a different visualization of it. But it's the same thing, green circles and black X's. We'd like to try to separate them. And in this case, we can't with a line. Now, support vector machines have an answer to this. What you do is you imagine that all of these data points are not on a flat plane, but they're on a sheet of rubber. And you can pick that sheet of rubber up and you can stretch it and bend it and warp it however you want. And you can probably visualize here that if you take that and bend it just right and slice it, you can separate out the good to eat fruit from the bad to eat fruit. And this is exactly how you would do it. If you can now, with a single straight slice, you can separate these things out nicely. This trick of bending your sheet of paper, of warping it, is called the kernel trick. And it refers to how it's calculated. But in practice, all you need to know is you can take this space that your data is in, this paper that it's on, and twist it and bend it however you want. You can take and hold down the middle and pull up all four edges. Or you can pull up all four edges and pull up the middle and leave a little ring low around the middle, or low around the center. Or you can take it and pull it up and pull it down and make it like an egg crate so that you can capture really irregularly spaced data, and with a single slice, you can separate it all out from each other. So the kernel trick is really powerful. And in fact, there is no limit to what you can do with this space to bend it. To illustrate another way that it's powerful, let's consider a slightly different problem. Now we have fruit. We don't care about the size, but we have 5 different colors. Green peaches are unripe. They're not yet ripe. Yellow peaches are ripe, so they're good. Orange fruit is an unripe plum, and a purple is a ripe plum. And then a black fruit is rotten. So the good ones to eat are the yellow peaches and the purple plums. Any other color is bad to eat. Now you can see that all of this data, it's just on one line, but there's no nice way to slice it to separate the green circles from the black X's. Now we can use the kernel trick. We can take that line essentially and bend it however we want. One way to do that is to just make a single bend in it, like a smiley face. And you can see that, great, we bent it, but still those circles and X's are not laid out so that with a single cut, we can separate them from each other. Now, the cool part about the support vector machine kernel trick is that you can come back and bend your space again in a different direction. So this represents a 2-dimensional kernel. And now it's not too hard to see that with the right slice, you can come in there with the plane and separate out those green circles from those black X's. Now, if you look carefully, you'll notice that this slice is actually not exactly the one you'd want. It kind of misses, but you can imagine where it would go to separate those out. So here we did two different warpings. We took our line and we bent it one direction, and then we bent it another direction. Because of the math, it's a little bit mind-blowing, but you can actually take whatever space your data is in, and you can bend it in an infinite number of directions to make it so that you can slice it and separate out your two groups of data. So that is pretty powerful stuff. This is what support vector machines do. They take and find the best slice that separates out two groups of data, and if your data is hard to separate, you can warp and twist your space until you find a way to separate it. Okay, so that's the explanation. Now comes the most important part. In addition to understanding the strengths of a method, you have to understand its weaknesses if you're going to use it well and push it to its limits. So, with support vector machines, issues include if you have data with lots of error. So if you notice, any time that we're finding a slice between two groups of data, the location of that slice depends almost entirely on the very nearest data points. The other ones, it doesn't matter if they're close to the margin or miles away from the margin. It's those nearest data points that determine exactly where that margin is going to be. And if each of those has a lot of error associated with it, then that error gets a really loud vote, more so than most of your data. So that is an issue. Another way that it can break is if you choose the wrong kernel. If you look back at the original data set where we were bending our paper like a sheet of rubber, if we bent it the wrong way, we would not be able to separate out our data sets. We had to bend it just the right way. That's choosing the right kernel. And the act of choosing the right kernel is an art. And it's done by trial and error and, after a while, by experience. And then finally, large data sets can break support vector machines. Calculating the kernel, some kernels especially, can be very expensive, take a lot of computing power. And so if you're not dealing with just hundreds of data points, but billions, then the amount of time to calculate those is prohibitive. So with large data sets, you have to stick with linearly separable problems. So you have to go back and hand engineer features that help your data get separated out. Help it so you can separate it with a straight line, single cut. So each of these requires a human in the loop to determine when it's a problem and to work around it. This is important to know. This means that support vector machines are powerful, but to get the most out of them, you need someone who has used them quite a bit and understands them well. This doesn't mean that they can't be used, but this is important to know when you're deciding what method to use on your problem. Now, taking a step back, that was a quick walk through support vector machines. Hopefully you understand it now a little bit better than you did before if you were new to it. And now going into another project, you know what you need to do to make good use of it. A comment on the process. We went through this together. There was no formal education, no coursework, no textbook, no professor, no permission granted, no special libraries, nothing purchased. This is all information that's out there. This is something that you can do with any tool you want. You can take and open the box and see what's inside. You can lift up the hood and you can see what the pieces are and how they work together. It's not an easy process, and sometimes it's quite painful, but it is something that you have at your disposal. And it's something that, in the cases of my key tools, I have found it very worth my while. So I encourage you, when you have something that you think you might need to use heavily, take some time, open the box, figure out how it works so you go from a grocery getter to a really high-performing race car. Thank you.